Welcome to the Deep Dive. Today we're going to be tackling a pretty fascinating piece of mathematical history,
Okay.
Book X of Euclid's Elements.
Right?
You might remember Elements as like your high school geometry textbook,
Right.
all those basic triangles and squares. But Book X, it takes us way beyond that.
Yeah.
It's been nicknamed the Cross of Mathematicians for a reason.
It has. That's a pretty fitting nickname. You know what's so fascinating about Book X?
What's that?
It grapples with the very nature of numbers,
Hmm.
specifically the ones that we call irrational numbers.
Okay. That sounds intriguing, but also maybe a little intimidating.
Right.
So what exactly makes Book X so difficult, and why should we even care about it today?
Well, imagine you're back in ancient Greece.
Okay.
They didn't have our modern concept of irrational numbers, like those decimals that go on forever without repeating. They couldn't
Yeah.
just write down the square root of 2 like we
Yeah.
can.
Yeah.
Instead, they had to understand these numbers through geometry as lengths and areas, and that's where things got really tricky.
Okay. I'm starting to see why this was a cross for those mathematicians.
Yeah.
Can you give us an example of how these tricky numbers or magnitude popped up in their geometry?
Sure. Picture a simple square.
Good.
Let's say each side has a length of 1.
Mm-hmm.
Now think about the diagonal of that square.
Okay.
Using the Pythagorean theorem,
Right.
we know the diagonal has a length of the square root of 2.
Oh, okay.
But the Greeks discovered something mind-blowing.
What's that?
You can't express the square root of 2 as a simple fraction or ratio of 2 whole numbers.
So you're telling me that diagonal, a real tangible line you could draw in the sand,
Uh-huh.
couldn't be measured accurately using the same units as the sides of the square.
Exactly.
No wonder this shook things up.
Yeah, that discovery was a major challenge to the way that the Greeks, especially the Pythagoreans,
Mm-hmm.
thought about the universe.
Right.
And that's where Euclid's Book X comes in.
Oh, yeah.
It lays out a systematic way to understand and work with these magnitudes, these irrational numbers,
Okay.
using the tools of geometry.
So Euclid basically created a whole new language for dealing with these unruly numbers,
He did.
all without using our modern algebraic symbols.
That's pretty impressive.
It is. He starts by defining key concepts,
Okay.
like what it means for magnitudes to be commensurable
Mm-hmm.
or incommensurable.
Okay.
Think of it this way. Two magnitudes are commensurable if you can find a common unit
Yeah.
that measures both of them perfectly.
Okay.
If not, they're incommensurable.
That makes sense. But how did Euclid actually figure out if two magnitudes were commensurable or not? Did he have some kind of mathematical test?
He did.
Really?
And it's surprisingly elegant.
Okay.
One of the first big ideas he introduces in Proposition X.1
Mm-hmm.
is a process for testing commensurability.
Okay.
It involves repeatedly subtracting the smaller magnitude
Mm-hmm.
from the larger one and seeing what happens.
So it's like a mathematical game of subtraction.
Yeah.
What's the goal of the game? The goal is to see if you ever get a remainder that divides evenly
Uh-huh.
into the previous number.
Hmm.
If you do, then the two original magnitudes are commensurable.
Okay.
But if you can keep subtracting forever, always getting a new remainder,
Yeah.
then you've got yourself two incommensurable magnitudes.
That's a pretty clever way to approach it, especially without having calculators
Right.
or even our modern number system.
Yeah.
And I guess Proposition X.2 builds on that idea, right?
Exactly. Proposition X.2 gives us a practical method for actually determining
Right.
if two magnitudes are incommensurable. And then he goes even further,
Right.
showing us how to find incommensurable lines in Proposition X.9.
So he's not just telling us what these magnitudes are.
Yeah.
He's giving us tools to identify and construct them.
Right.
But let's be honest, this is already getting pretty complex.
Yeah.
Why did Euclid go through all this trouble?
Yeah.
What was the point of categorizing all these different irrational magnitudes?
That's a great question.
Yeah.
And it gets to the heart of why Book X is so important. Remember, for the Greeks, geometry wasn't just an abstract subject.
Right.
It was deeply connected to their understanding of the world, to art, architecture, and even philosophy.
So understanding these irrational magnitudes
Right.
wasn't just a theoretical exercise.
Right.
It had real-world implications.
Absolutely. Think about it.
Yeah.
If you're trying to build a temple
Okay.
or design a mosaic
Right.
and you're dealing with proportions and ratios, you need to understand the nature of the magnitudes involved.
Okay.
Are they rational, or are they these more complex irrational magnitudes?
Right.
Knowing the answer is essential for achieving the desired harmony and precision
Okay.
in your design.
It's like trying to bake a cake without understanding the difference between a teaspoon and a tablespoon.
Right.
You might end up with a very strange cake.
Precisely. And that's just one example.
Right.
Euclid's work in Book X laid the groundwork for a deeper understanding of geometry and its applications.
Yeah.
But its impact goes even further.
It actually had a profound influence on the development of algebra,
Really?
even though it was presented in a purely geometric form.
Yeah, so you're telling me that this geometric deep dive into irrational numbers actually helped shape the way we do algebra today.
It did.
I'm really curious to hear more about that connection.
Well, that's a story for part 2.
Oh,
But before we move on,
yeah.
let's make sure you have a good grasp of the foundation Euclid builds
Yeah.
in these early propositions of Book X. Remember, he's giving us a way to understand and categorize magnitudes.
Yeah.
That can't be expressed as simple ratios.
Right.
And he's doing it all through the elegant logic of geometry.
So we've seen how Euclid identifies incommensurable magnitudes using that clever subtraction method.
Right.
But where does he go from there? How does he start to bring order to this seemingly chaotic world of irrationality?
Wow.
Join us next time as we delve deeper into Book X and uncover the fascinating system Euclid creates to classify these elusive magnitudes.
Welcome back to our deep dive into Euclid's Elements, Book X.
Yeah.
In part 1, we talked about how Euclid tackled the problem of magnitudes that couldn't be expressed as simple ratios.
Right.
Those we call irrational numbers today. He gave us a way to identify them
Yeah.
using that clever subtraction method and hinted at the challenges they posed to the Greek understanding of mathematics.
Euclid realized he needed a way to classify these irrational magnitudes.
Okay.
It wasn't enough to just say, okay, this one's irrational and so is that one.
Right.
He wanted to understand the different types of irrationality, the different ways these magnitudes could be constructed and combined.
So it's like he was creating a field guide to the world of irrational numbers.
Exactly.
Instead of birds or butterflies, he was categorizing different species of irrational lines.
That's a good way to put it. And that's where those binomial and apotemy lines we briefly mentioned come in.
Right.
They're essential to Euclid's classification system.
Okay, to be honest, that's where I started to get a little lost. Can we unpack those a bit more?
Sure.
What are the key distinctions between binomial and apotemy lines, and why are they so important to Euclid?
Let's start with the binomial lines. Imagine you have two lines
Okay.
that are what Euclid calls commensurable in square only.
Hold on, commensurable in square only. That sounds like a mouthful.
Yeah.
Can you explain what that means in a way that doesn't make my head spin?
Think of it this way. You have two ropes.
Okay.
One is twice as long as the other.
Okay.
If you square the length of each rope,
Right.
you get a nice, neat ratio 1:4.
Okay.
The squares have a simple relationship, but the ropes themselves can't be measured by a common unit. That's what it means to be commensurable in square only.
Okay.
The squares have a rational relationship, but the lines themselves do not.
Okay. I'm starting to get the picture. So a binomial line is formed by adding two of these lines that are commensurable in square only.
Precisely. And Euclid identifies 6 specific types of binomial lines, each based on the specific properties of those two lines being added together.
Okay.
It gets a bit technical, but the key takeaway is that each type represents a distinct way of combining these special irrational magnitudes.
And what about those apotemy lines?
Right.
How do they fit into all of this?
Think of apotemy lines as the opposite of binomial lines.
Okay.
Instead of adding two lines together,
Right.
an apotemy line is formed by subtracting one line from another.
Okay.
And just like with binomials, those lines have to be commensurable in square only.
So it's like Euclid is exploring all the different ways to put these irrational magnitudes together and take them apart.
Yeah.
But why go through all that trouble? Why does it matter what kind of irrational line you're dealing with?
Remember, Euclid is trying to create a system, a way to organize and understand this whole realm of irrationality.
Okay.
He shows that each of these binomial and apotemy lines, when multiplied by a rational line,
Okay.
produces a very specific kind of irrational area. This classification system is crucial for understanding how these magnitudes behave.
Right.
in different geometric constructions.
It's like he's giving us a set of tools to navigate this uncharted territory of irrational numbers.
Right.
Tools that were especially important back then.
Yeah.
When they didn't have the algebraic language we use today.
Exactly. And what's amazing is that even though Euclid was working within the constraints of geometry, his insights had a huge influence on the development of algebra centuries later.
You mentioned that connection before.
Yeah.
Can you give us an example of how Euclid's geometric approach to irrationals actually paved the way for modern algebra?
Well, think about someone like Fibonacci, who's famous for introducing the Arabic numerals we use today.
Right.
He was deeply interested in problems involving proportions and ratios, problems that often involved irrational numbers. And he drew heavily on Euclid's work in Book X to solve those problems.
So even though Fibonacci was working with numbers in a more symbolic way,
he was still building on the geometric foundation that Euclid laid out.
Absolutely. And it goes even further.
Okay.
Cardano, who was a major figure in the development of algebra in the 16th century, also relied on Euclid's ideas about irrational magnitudes when he was exploring the solutions to cubic and quartic equations.
It's incredible to think that a book written over 2,000 years ago could have such a lasting impact on a field as abstract and seemingly unrelated as algebra.
It really is. And it highlights the fact that mathematics isn't just a collection of isolated formulas and procedures. It's a tapestry of interconnected ideas with insights from one area often shedding light on seemingly unrelated areas.
Speaking of interconnected ideas, we've been talking about binomial and apotemy lines, which are already pretty complex. But Euclid doesn't stop there, does he?
Not at all. He takes those binomial and apotemy lines and uses them to construct even more complex irrational magnitudes. It's where things get really mind-bending.
Okay, now I'm really feeling like Alice tumbling down the rabbit hole. Lead the way. I'm ready for more. Welcome back to the Deep Dive. We're exploring the fascinating and complex world of Book X of Euclid's Elements. Where he takes us on a journey through irrational magnitudes. We've talked about how he identifies these magnitudes, classifies them using those binomial and apotemy lines. And even touched on how his work influenced later mathematicians like Fibonacci and Cardano. We've covered a lot of ground, but I have a feeling things are about to get even more intense.
They are. It's quite a journey, and we're about to enter the most challenging part. Remember those binomial and apotemy lines we discussed?
Yes.
Well, Euclid uses those to create even more complex irrational magnitudes.
Okay, I have to admit, this is where my brain starts to feel a bit overloaded. We're talking about magnitudes that are basically the square roots of areas that are already irrational, right?
You're not going to... It's definitely a leap in complexity, but stick with me. Imagine you have a rectangle with sides that are irrational lengths. Specifically a combination of those binomial and apotemy lines we talked about. Now picture trying to find the length of the diagonal of that rectangle.
Okay, I'm visualizing it, and I'm already sensing that the length of that diagonal is going to be a pretty messy, irrational number.
You're exactly right. That diagonal represents one of those more complex irrational magnitudes that Euclid explores in the later propositions of Book X. For example, in proposition X.54. He shows how to construct what he calls a second bimedial.
A second bimedial. I'm intrigued, but also a little intimidated by that name.
Think of it as a new entry in Euclid's comprehensive field guide to irrationality. He creates this second bimedial by taking a rational line and multiplying it by a specific type of binomial line.
So he's combining a simple rational line with one of those more complex irrational lines we discussed earlier, and that creates this whole new type of irrational magnitude.
Exactly, and he doesn't stop there.
Of course not.
Euclid meticulously describes the construction of numerous other complex magnitudes. It can get very technical, but the important takeaway is that he's systematically exploring all the different ways. These irrational quantities can be combined and manipulated using the tools of geometry.
So it's like he's not just randomly creating these magnitudes, he's revealing a hidden structure and order within this seemingly chaotic world of irrationality.
Precisely. And that's one of the things that makes Book X so remarkable. Euclid demonstrates that even these seemingly elusive and complex magnitudes can be understood and categorized within a logical framework.
This makes me think about how we learn math today. We often approach irrational numbers through algebra, focusing on symbols and equations. But Euclid's approach is so visual, so grounded in the shapes and relationships of geometry. Do you think we lose something by neglecting that geometric perspective?
That's a great question, and one that mathematicians continue to debate. Some argue that Euclid's geometric approach gives us a deeper, more intuitive understanding of irrationality.
Okay.
It allows us to see these numbers not just as abstract symbols,
Right.
but as tangible lengths and areas.
It's like the difference between reading about a forest and actually walking through it.
Yeah.
You experience it in a whole new way.
Exactly.
Yeah.
And that direct experience can lead to a deeper understanding.
Yeah.
But there's also no denying the power of the abstract language of algebra.
Right.
It gives us a level of precision and efficiency that would be very difficult to achieve through pure geometry.
So it's not a matter of one approach being better than the other, but rather recognizing the strengths and limitations of each.
I think that's a great way to put it.
Yeah.
And perhaps the most valuable lesson we can take from Euclid's Book X is this. When we're faced with something that seems complex or even impossible to grasp,
Yeah.
sometimes the best approach is to break it down into smaller, more manageable pieces.
Okay.
Explore the relationships between those pieces, and look for the underlying patterns and structures that connect them.
That's a great takeaway, not just for mathematics, but for any field of study, or even for life in general.
Absolutely.
Well, we've covered a lot of ground in this deep dive into Euclid's Elements, Book X.
We have.
We've explored how he defined and classified irrational magnitudes, tackled increasingly complex constructions,
Right.
and even touched on the philosophical implications of his work.
And what's truly remarkable is that even after more than 2,000 years,
Right.
Euclid's work continues to inspire and challenge mathematicians. It reminds us of the enduring power of human curiosity,
Yeah.
the elegance of logical reasoning, and the beauty of uncovering hidden patterns in the world around us.
So the next time you encounter an irrational number, whether it's pi or the square root of 2, remember that you're not just dealing with a decimal that goes on forever.
Right.
You're touching on a concept that has captivated mathematicians for centuries. A concept that Euclid, using only the tools of geometry, helped us to understand. Until next time, keep on diving deep.